Okay. Okay. So let me start with the philosophical questions that by now you have understood I like. Why are we here? And we are here because the atmosphere protects us against the harmful high energy radiation and particles, among them X-rays. So that's the reason why we need powerful and rich space agencies all over the world to send satellites in space in order to detect X-ray from cosmic sources beyond the screen of the atmosphere. Now, one of the questions that any politicians in any countries want to understand is why do we need so many different X-ray satellites in space? Now, they are basically do all the same thing. They are all detecting X-rays. So, of course, this will be, the subject of the whole conference. But the way I approach this question in this workshop is to make a short summary of how we focus X-rays, so how we create images in X-rays, how we detect X-rays. And these two parts of my presentation are essentially primarily instrumental for me to introduce which are the basic quantities describing the performance of X-ray instruments that you need to be familiar with to understand what you're doing. So let's start with the focusing. Now, focusing, we use, principle of focusing is total reflection. So we need to have a system which is able to reflect X-rays using the total reflection principle. And if you look at the basic physics of total reflection, and if you put the numbers, the wavelengths that corresponds to a typical X-ray photons, which is of the order of tens of angstrom, you immediately see that in order to achieve the reflection from a surface, from an optical surface of X-ray photons, you need to have very low angles of incidence. We talk of grazing incidence. Now, grazing incidence requires that you have to have an optical system that essentially whose photons are hitting your reflecting surface as an angle which is essentially lower than 1 degree. And the reflectivity is a strong function of the value of this angle. This is shown in the left plot of this slide, which shows as a function of energy, be careful, the energy is essentially goes from 0 to 8,000 electron volts, so 8 keV. keV, kilo electron volts, is essentially the basic units of energy that we use in X-ray astronomy. And this compares the reflectivity of a surface covered with iridium, one of the elements which is mainly used for optics in X-ray astronomy, for different values of the incident angles. 2 degrees, 1 degree, 0.5 degrees. And you see the difference is enormous. So the more grazing incidence you need, the lower the grazing incidence, the higher your reflectivity. This has immediately a consequence. You will see that, since if you have grazing incidence, you have a very low effective reflecting area. So that's why if you look at an X-ray telescope by variance to an optical telescope, you will see very often nested shells, because we want to enhance the reflective effective area that in each shell is relatively low. Or you create intelligent tricks to have multiple reflecting surface. And that will be the subject, one of the subjects of my last lectures on the future of X-ray astronomy.
Another thing that you have to notice.
Another thing that you notice that that's me. Sorry. That's me. Focusing higher energies requires longer focal lengths. This is why one of the 3 missions we are going to deal with in these days has an extended boom. And I will leave you to guess which one it will be by the end of the day. There is also a relationship between the focal length and the field of view. If you have a shorter field of view, a shorter focal length, you have a higher field of view. Correspondingly, if you have a longer focal length, you have a smaller field of view. So it's very difficult to have an instrument with high X-ray reflecting power, so operational in the highest possible energy range where the focusing optic is possible, and survey capabilities. I'm sure that Christine is going to tell more about that in their presentation later today. Now, since the 60s, there is a sort of reference geometry that has been used in all X-ray telescopes to focus optics, which is the so-called the Volter 1 geometry, which is a combination of a paraboloid surface and an hyperboloid surface. And this allows you to achieve the best focusing power and also the best correction of optical aberration. Now, there are different ways of implementing this kind of perfect geometry. There are conical approximation, often used for the paraboloid surfaces, but these are by far and large second-order technical details for you. But the important point is that in reality, if you don't have very strict requirements on the quality of your image, you actually, the paraboloid surface are sufficient for you to focus a light from a source at infinite to the focal plane of your detector. So in fact, an instrument like NICER that doesn't have strong requirements on the quality of the image, because as I show you later, essentially the NICER detector are single pixel detectors. They can actually get rid of one of the stage and just having reflection by the paraboloidal surfaces, which make, of course, the technology of construction of these things much easier. Something that it will be all clear often to you in my last day presentation. Most of the technological achievement that we have obtained in space, in space science, are limited by money. So if you can do something cheaper, this is always welcome for every space agencies. Space agencies don't like wasting money. Now, in the history of X-ray astronomy over basically half a century has been limited, if you look at focusing measurements, to the 10 kV band. So we had optical imaging instrument, focusing telescope since the 80s, probably. But none of them was able to have sufficient collective area above 10 kV. This is a great deal of the science in X-ray astronomy was done below 10 kV until a pivotal moment in the history of X-ray astronomy when NuSTAR was launched. Now, it's fair to say, as it will be clear from the science presentations, that this is also the wavelength until 6, 7, 8 kV, where you have the strongest atomic emission and absorption lines in X-ray plasmas. So, there was a nice match between technological capabilities and science requirements. But as Christine is going to say, and surely later today or tomorrow, there are plenty of new science that focused optics above 10 kV could have opened and did open when, for the first time, the technical of multi-layers of reflecting matter was implemented in space. The trick is, if I have lots of the layers of materials that are able to reflect the light, I can, in a sense, accommodate, I can create a trick where I increase my effective area by creating constructive interference among the reflection of these layers. That was the trick that was used in NuSTAR in order to enhance reflectivity above 10 keV and achieve an effective area which you can't even compare with Chandra XMM, with Suzaku, with ASCA, with Bekosax, with all the instruments. No, Bekosax didn't have optics that were flying X-ray optics before that. So this is a plot, one of the plots you have to get familiar with. On the y-axis is a quantity called effective area, which has the unit of an area. It's not the geometrical area of the optics, but it's a quantity that takes into account all the components that eventually make up the capability of an instrument plus optics, so optics plus detector and instrument to detect X-ray photons as a function of energy. And the orange line is NuSTAR compared to all the active and still active instruments at that time, except Suzaku, with optics, so with focusing optics. And there is, of course, no comparison in the range above 10 keV. Now, something that I'm not stressing, why I'm stressing so far the concept of optics? You would say, well, there are several ways of, detecting. You have detectors in X-rays. Can't you simply put your detector in, looking at the sky and see what happens? Why do you want to focus? Now, just to make sure, I think this is a trivial question for most of you. But optics, focusing optics is the key way in order, first of all, to do images that allows you spatially resolve analysis of diffuse structure in the sky. And you will see there are many objects in the sky that are diffuse, that are extended, large scale structure. And if you don't have optics, you can't really understand what's happening in them. Supernova remnant, galaxy cluster, galaxy groups, all this kind of stuff, all this stuff. I work in Asia. And, but there is a more fundamental reason why you want to focus. The reason is that if you are able to concentrate your photons in a small region of your detector, you are enormously increasing your signal to noise. You reduce the background underlying your source. The background is always the first order proportional to the volume of your detector. So if you just put a detector in space and you tell me all the photons that you see, you will get a lot of background photons you're not interested in, proportional to the volume of the detector, and it will be very difficult to get a nice signal to noise. By focusing, you actually get the best ratio between the source you're interested in and the background photons you just want to get rid of. So how do we detect X-rays? Well, fundamentally, the process that you're using is photoelectric absorption. I show here two plots as a function of energy of the attenuation coefficient for two materials, silicon and cadmium tellurium. The reason why I've chosen these two elements will be clear in a moment. Now, be careful now at the X-ray, at the X-axis units in this case. These are kilo electron volts directly. So since, NuSTAR and XMM, they go up to 10-ish kV, NuSTAR goes up to 70-ish kV. What you are actually looking in both plots is just the left part of the plot. That's where the instruments are effective and where is photoelectric absorption dominates. So we need to have a detector capable of using the photoelectric absorption to create quantities that can tell us that a photon is interacted with our detector, and maybe that we can also derive where and with which energy and when. Now, the simple concept since the beginning of X-ray astronomy has been simply ionization chamber. So an incident particle is coming, it's filled with a certain type of gas, typically a relatively inert gas. and it creates a track, a ionizing track created by photoelectric effects. So you have an ejection of a photon, and positive ions remains left after the electrons has been ejected. And then if you put an electric field within this gas, you can essentially collect the electrons that have been produced by this interaction track. And there is a sort of proportionality between the number of electrons, so the current that you measure, and the energy of the incident photons. You can reconstruct the energy of the incident photons. In this scheme, there is no mention, I've not mentioned at all where the event happened. The event can happen everywhere in the camera, and this kind of very simple concept does not allow you to have a very accurate positional reconstruction of the events. But the problem with this scheme is that this primary ionization produces very weak signals of just an amount of few millivolts, which is very difficult to detect. So typically, these ionization chambers were coupled with systems, electrical system capable of amplifying the charge when the charge was read, in order to get an amplification factor of the order of hundreds, thousands, several hundred thousand. This very simple concept has been the workhorse of X-ray astronomers for decades. But the great, the big jump ahead was when X-rays CCDs were used. And for the first time, they were used on a Japanese-led satellite called ASCA in the middle of the 90s. Now, CCDs are, nowadays an extremely common thing that we have in all of our digital devices, but they are, of course, optical CCD. So there are some difference between the way optical CCDs works. And, well, of course, you are familiar if you are optical astronomers to the CCD in optical astronomy, but, there are certain important difference in the way X-ray CCDs work with respect to optical CCDs. Now, the concept is very simple. You have photons interacting in a semiconductor layer via photoelectric absorption, and they produce clouds of electron and holes, so positively charged ions. And these pairs, well, what matters is eventually the cloud of electrons, which is what eventually we're going to measure. Once again, there is a certain proportionalities between the number of electrons that are produced and the energy of incoming photons. So if I'm able to measure accurately the number of electrons that a given X-ray event has produced, I can very accurately reconstruct the energy of the event. And but CCDs do also something more for you. I can organize the CCDs in pixels. And so if I know in which pixel a certain event has happened, and I know where my telescope is pointing through the satellite information, I can exactly pinpoint where the event happened. So I can do accurate imaging reconstruction. Now, once the event happens in a given pixel of your semiconductor, they are of a little use, these electrons, unless you're able to read them. So what typically happens in this system, you apply a modulated potential in order to shift these electron clouds from one pixel to the next through a row, through a column, up to the point where there is a reading system, an amplifier that is able to read the number of electrons and convert, therefore, the event into an electric signal that contains all the of holes. So, the tendency would be to recombine very quickly. So you have to manipulate the semiconductor in certain special way. Essentially, we have to add sometimes some impurities that essentially create, in a stable way, regions that have an excess of negative charge, electrons, and regions that have an excess of positive charge, holes or positively ionized ions. The former are called N-type, and the latter are called P-type. P-type. Yeah, thank you. For lack of a better name. And now if you join them, okay, at the junction, free electrons, they find their friends, their holes, and they recombine. And this creates a layer of positive and negative charge that prevents electrons and holes outside this region from recombining. And it is this depletion region, this is called this way, which is enhanced by applying appropriate voltage to the system, which is where actually the detection of X-ray photons happens. So this is a scheme, a conceptual scheme of a CCD structure in Chandra, for instance. I just use that because it's the best scheme I found on the internet. And the region where the detection is happening is this depletion region, is this intermediate region, where you have very little diffusion of the, very little lateral diffusion of the charge. And therefore, once the charge is concentrated very well on a pixel. Now, of course, there are also events that are so energetic that can go through this layer and reach an area below where actually there is a possibility of a larger lateral diffusion. And this means, it immediately leads to the fact that one of the things we have to deal in X-ray astronomy is that while ideally we would like all our events to happen in a given pixel, because one pixel means one position in the sky, this almost never happens. Most of our events are detected on a set of nearby pixels, what is called grade in some missions, pattern in XMM Newton. And we have to be able to reconstruct from a structure of different pixels what actually, that they all belong to the same event, so which is the total energy of the event. You immediately see that if a certain event create a signal in various pixels, the total energy of the event is the sum of the energy of individual pixels. So I must know the shape of each event if I want to reconstruct the energy correctly. If I know, that's something that I have to deal with via data analysis later. From the point of view of the physics, I have my cloud of electrons, and I transfer the cloud of electrons through this variable, time variable potential to an amplifier where it is read. And so I know what is the signal. Another thing I would like to stress at this point, which is another fundamental concept for you to understand the performance of CCD detectors, is that transferring the charge from the position where it was created, the cloud, to the amplifier, to the reading node, does not come for free. You may lose electrons over this process. In fact, you lose electrons over this process. And you lose a high number of electrons because, I understand in optical CCD, one optical photons create basically one electron. And so, in fact, that's the reason why, if I understand correctly, you work essentially most optical CCD in imaging mode, in frame accumulation mode. But in the case of X-ray astronomy, each event creates thousands of electrons. I show you the constant. The constant was, there is one electron every 3.7 EV. So if I have a photons of 60 keV, it's creating almost 2,000 events. So even if I lose 10 to the minus 5 events for each step of my transfer, but my system has thousands of pixels, I can easily lose hundreds of electrons. Well, hundreds is too much, but tens of electrons in the process of reading the cloud of electrons in a CCD like the XMM Newton epic CCDs. This is a very important phenomenon. You see what the risk is. I read a certain number of electrons and I say the energy is number of electrons times 3.7 eV, but that's not true because I have lost the sum of them and actually I don't know how many I lost. And one of the things that have to be most accurately calibrated in X-ray astronomy is charge transfer inefficiency. The name says it all. Now, another important thing in XMM, you have two types of CCD. One is the PN type, another one is the MOS type. The main difference from your perspective is that the epic PN are back illuminated. So light is coming from below in this scheme. But the epic MOS are front illuminated. So there are cameras where the light is coming from above, which means that some of the photons actually never reach the depletion region of the CCD. They are absorbed by the gate structure on top. And this is seen if you look at, for instance, the quantum efficiency of an instrument, which is the quantity that tells you essentially only for the detector the efficiency in detecting events, in detecting photons. And for instance, on the right side of this plot, you see the comparison as a function of energy. So the energies are, in both cases, from 0 point something to 10 keV. MOS is the top, PN is the bottom. MOS is front illuminated, PN is back illuminated. And the quantity is always between 0 and 1 on the y-axis because it's essentially a detection efficiency. And just by eye, you probably cannot see well the scale, but just by eye, the two plots have a similar scale. You immediately see that PN has a much higher quantum efficiency. So when you use XMM Newton data, and if you want to choose which spectrum with the highest signal to noise, you have to analyze all the data, of course, but the first choice will be always almost invariably the PN because it will have more photons. There are other reasons why you may use MOS in some cases, but I'll talk about this, or Aitor probably will talk about this later. Another phenomenon you have to be aware, in particular with CCD data, is fire. Now, these CCDs are not read continuously, the CCDs of XMM. Essentially, there is a period during which the charge is accumulated, or the photons are read, and so charge is accumulated in various pixels, and then an interval when the CCDs are read. So if you have a very strong source, it may happen that two independent photons, fall on the same pixel during an interval where the CCD is accumulating charge. But the system does not know about it. It's not so intelligent to know which is which. The system registers a certain number of electrons below a given pixel, and the system doesn't know by itself that these electrons have been created by two events simultaneously hitting the CCD. Simultaneously means within the same accumulating interval. And this creates a phenomenon which is called pileup. Pileup has two effects. First of all, it makes you calculate the wrong flux because you believe that a certain number of electrons have been created by one photon, but they've been created by two photons or three. And therefore, your flux is wrong. Actually, it's lower. You believe that less photons have been detected than in reality. But there is the second, the more important effect, which is spectral distortion. If I detect several photons at the same time, and I just measure the collective cloud, the collective number of electrons generated by n events, I will sum up the energy of individual events. So instead of getting a spectrum of, say, 3 events of energy 1 keV, I will get 1 event of energy 3 keV. So I have less flux, but a harder spectrum. And pileup is a true problem, as Aitor is going to show you for the XMM case very soon. The best way is to avoid pileup. And avoiding pileup is the main reason why the XMM Newton EPIC instruments, they have different operational modes. Sometimes we image the whole field of view, that is the field of view that covered by our detector. In the case of the EPIC PN shown here is 30 degrees, 30 arc minutes times 30 arc minutes. But if you look at a smaller region of the sky, you can read your CCD faster. And if I can read the CCD faster, I can deal with sources with a higher count rate without pileup. And that's why we have large windows, small windows, and even modes where you don't create images any longer. You are just accumulating photons, but you lose completely the information of where the events are lost. It is the price you pay for special timing modes that where actually have no imaging capability. Now, I talk a lot about CCD, that are the instruments on XMM Newton. NuSTAR doesn't have CCDs as such, but solid state detector. It's an array of cadmium, zirconium, tellurium crystal, zinc telluride crystals. Okay, good, thank you. And of course, since I know very little of them, I leave Kristen to talk about that. And also nicer detectors are silicon drift detectors. Basically, they are 56 single pixel detectors, each of them coupled to a concentrator. And that's, remember I mentioned that there is no imaging requirement associated with nicer, essentially for this reason. Now, that's now the point where it comes the point where you have to concentrate more, because these are quantities. I'm going to show you the few quantities that you need to get familiar with since the very beginning. The easiest probably for you to get hold on if you have prior experience with astronomy in other wavelength is the point spread function. So it's the quality of your imaging. Point spread function is the shape of a point-like source at infinite in your detector plus telescope system. And the big image is what you can get with Chandra. Chandra, as you probably know, has the best image quality telescope currently in operation, with an half energy width of the order of half arc seconds. And half energy width is the width of an image of a point-like source at infinite, where you have half of this energy of half of your events are collected. And I compare it with the point spread function of XMM Newton in the top right corner, and an instrument with an even lower resolution, Suzaku, which is representative of the type of optics that JAXA, the Japanese Space Agency, actually they are American optics, built at Goddard, that the Japanese mission typically carry. And you immediately see, of course, that's an image that tells more than 1,000 words. That's why Chandra is the workhorse if you want to do very detailed X-ray imaging, energy-dependent X-ray imaging of your source. But maybe more important for you to get familiar with is the encircled energy fraction quantity, which is an alternative convenient way to represent the point spread function in one dimension. Essentially, the x-axis is radius, and the y-axis is the fraction of photons accumulated within that radius. And these are the encircled energy fractions for XMM Newton, from which you see that, half of the energy, it's 0.5 level, is around 15 arc seconds, you see in both cases. There are small differences related to the quality of the mirror and also to the pixelization of the instruments. Now, something that if you work with XMM Newton, you should be dramatically aware of, but also if you work with NuSTAR, is that these are the numbers of the PSF at the center of the field of view, or better said, where your optical axis is located. But the PSF, the image quality in X-ray astronomy degrades dramatically in off-axis. It happens for XMM. I've shown here the example of Chandra, because, you know, Chandra that has a point spread function better than 1/2 than axis. If you go at the edges of the field of view, you get actually point spread functions that are significantly worse than XMM Newton. The degradation of axis is very extreme. And the same kind of degradation happens with the star, but more than the degradation in terms of quantity is the fact that point spread functions are heavily distorted. They are no longer nice radially symmetric, azimutally symmetric shapes. So this means that if you want to analyze extended sources with which are very off axis in XMM, for instance, that's searching for lots of troubles. It's not an unsolvable problem, but it's a difficult problem to deal with. Also because all these shapes are energy dependent. Another important quantity is the energy resolution. Now, the energy resolution is conceptually very simple to define. Is a measurement of the width of the monochromatic spectrum that your detector measures. So in X-ray astronomy, if you're, either going to go gratings and going to go microcalorimeters, but most of the detectors we are going to deal with in these days, they have a relatively poor energy resolution, which means that if I measure a monochromatic line of energy 1 keV, my detector is identifying the photons corresponding to energies that are not 1 keV. Only a small fraction of them will correspond to 1 keV. Some of them will correspond to lower energies. Some of them will correspond to higher energies. And the shape of this distribution is a nightmare and is energy dependent. So this is how actually, this is the spectrum, a conceptual spectrum of a 1 keV line observed by the epic PN. It's the conceptual spectrum of an energy, of a line at the given energy, and the energy is given by the colors. We go from 0.3 keV, the black line, to 6 keV, the magenta line. And on the x-axis, I just show the ratio between the channel where the line should be located according to the theoretical relation between the number of events and the energy of the incoming photon, and the truly detected energy by the detector. So look at the black line, for instance, the dashed line. This is telling you that if a photon of 1 keV impinge my detector, there is a not negligible, actually rather large probability that the cloud of electron that I measure in my detector corresponds to energy of half, 0.5, 20%, 0.2, 10%, 0.1. And you have to imagine X-ray sources have continuous spectra. So imagine deconvolve the energy of a given event, measured energy, the energy of a given event using the measured PI channel, knowing that you don't have a one-to-one correlation between the spectral channel in your detector and the incoming energy. It's a nightmare, but there is people who have done the job for you, and you can use what they have done. This is the concept of redistribution matrix phi, which is very common in astronomy, and you will get familiar with it at the latest in my presentation on X-ray spectral analysis tomorrow, but probably earlier with Sunil later today. I've already showed you the effective area. Just just to remind you, effective area is the collecting power of your telescope plus detector as a function of energy. And but another aspect that is for you important if you work with both XMM and Mustard data, the effective area is not the same over the field of view. There is a sort of shadowing effect, self-shadowing effect in all X-ray optical systems, making that the effective area off axis, far from the optical position of the optical axis, is lower than at the center. And so if you look at sources off axis, the real effective area is, in the case of XMM, for instance, at the distance of 15 Arrhenius from the center, is less than 50% than the effective area on axis. So when you work off axis, you have several troubles. You get less photons, you have a much more distorting imaging profile. You know, I'm not discouraging you from working with off-axis sources, but you know, if you work with off-axis sources, of course, or with extended sources, very extended sources, your life will be more exciting. I don't want to say more challenging, I say more exciting. That's all I wanted to say for today. So I thank you for your attention, and I'm glad to take any questions you may have. Thank you. Yes.
Thank you very much for the presentation. Some of us are coming with X-ray astronomy. So such applications like technique.
Oh.
Be explained.
Oh, that's a very good point. You are right.
Matteo, can you repeat the question? Because
Yes.
I'm not sure that it's recorded.
You are right. I didn't think about that. Thank you. I gave this presentation. First of all, I repeat the question. The question is, many of us are not X-ray astronomers, so we are not all aware of the shortcomings. That's a very good point. Normally, I always explain them, but you're right. He made the example of EPIC, and because EPIC is one of the instruments on board Dixon and Newton, and of course, this comes after, you know, to be logical to talk about EPIC after the presentation on Dixon and Newton. It's a very good point. I gave this presentation once, and this point was not made, so I didn't correct it. But I reckon it's an issue, and I thank you for your attention. In specific case, EPIC is the European photon imaging camera, is one of the CCD instruments of this thing. Is there any other shortcomings you would like to explain? Yeah, but you know, if there is anyone that you mean I've not understood anything unless you tell me what this means.
My last question. Pixel and then six and probably photon. Maybe every pixel is that number of photons. The whole system is parallel.
So your question is why are X-ray detectors being designed to be photon counting?
I'm just asking how carefully are they designed in such a way that each pixel only receives a photon?
Yeah. Well, but you know, this is actually very good to have. You know, the question is why were the detectors designed in such a way to get that one pixel gets one event? Well, they have been designed carefully this way because knowing so being able to associate a pixel to a given event is very important because it can tell you where the event happens. If I have just a system that just tells me in this volume an event happened, but I don't know where. No, it can happen on a very large area of the sky, and this doesn't help me in doing detailed spatial analysis of X-ray sources. And the second reason is, if I can pinpoint exactly in the array of pixels where the event happened, at that point, I can highly decrease I increase the signal to noise because the number of background events corresponding to that pixel is much smaller than the number of background events accumulated over the whole detection. Remember, as an order of magnitude, the background scales always the volume of the detection. So if I can give in my analysis only the background which is detected in a very small region of the detector, I can detect a much fainter source. So this design is actually clever, and it's designed this way in order to achieve these two goals.
We find different modes.
Yeah, and then why we have
observation. because we are dealing with all kinds of energies and all kinds of photons. We want the camera to be able to detect the photon with low energy, but also with high energy.
Maybe we can take question from him. Yeah.
It's not arbitrary numbers, right? It has some equivalence like of 300 centimeters square for
Yeah.
So I wanted to know what that is like. What that is exactly represents.
Yeah. So this is an area, but it's an area which is the product of the geometrical area of the mirror times a certain number of factors which represent the efficiency of detections of your telescope and of your detectors. For instance, not all the photons impinging your telescope at given energy are detected, because only those that are only a fraction related to the reflectivity of the material, which is the reflecting surface of the telescope, are actually going to the focal plane. And in the focal plane, the detectors, not all the photons reaching the detector, they are revealed, they are detected by the instrument. Some of them are lost. So when you take the geometric area of the mirror in centimeters squared,
Maybe explain geometric area.
Geometric area is really, if it is a square, if it is a circle, radius square times 5. That's the geometric area of the mirror. Then I have to multiply for a series of factors comprised between 0 and 1. And this multiplication leads eventually to the definition of effective area. So a given energy is the geometrical area of the mirror in the Euclidean sense, the dead energy times the efficiency of the telescope and the efficiency of the detector. So the efficiency of the detector includes the quantum efficiency, includes the filter transmission, includes the bedtime effect, includes lots of different things. Some of them will be explicitly dealt with in the data analysis section because you need to know about these effects. But some of them you don't really need to know. You just have the effective area at the end, which is the product of everything else, and you just use it. But that's the reason.
So for that, how do we calibrate? We calibrate with some simulation, or do we do some map testing of that?
Okay. Okay, calibration is what?
We calibrate. You don't calibrate.
You don't
We
calibrate.
use our files.
Yeah. You don't calibrate. Yeah. The way, okay, calibration is in itself another talk of several hours. And Christine, once again, is the right person to ask because she's coordinating a group of several tens of scientists whose salary is primarily paid to do calibration. But in a nutshell, the good news for you is that in 99.9% of the cases, you don't need to do the calibration. There are people who have prepared files describing the transfer function of the instruments in energy space, in imaging space, in timing, and you use this file to process your data and therefore to interpret the digital signal in the proper way. Why I mention these quantities? Because while you don't need to calibrate the instrument, if you don't understand the concept of effective area, if you don't understand the concept of redistribution matrix, and I've not been able to explain it, but it will be repeated time over and over again with the question. If you don't understand the concept of point spread function of better than circular fraction, these are concepts that you use to interpret it. That's why we introduce them so early. But you don't need to calculate them. Carlos has done all the job for you. Good luck. Hey.
Yeah, I was just interested in comparing optical CCDs and X-ray CCDs, where, of course, in optical CCDs, the amount of detection is only really dependent on the flux in the optical, not the energy. Quite different to the X-rays. And of course, in optical CCDs, we typically back illuminate thin them, use different sort of resistivity silicon to promote the sort of efficiency of low energy optical photons. In the case of X-rays, obviously, if you just illuminated one of those CCDs, the X-rays would just go straight through the device, would it not? So I'm sort of interested in knowing how the CCDs are sort of developed for X-ray astronomers by the same companies, right? But it's specifically for X-ray detection.
Depends. Some of them are produced by companies. Some of them are developed in-house by institutes. In fact, for instance, the PNCCDs, they are produced by a company which is actually a spin-off of a laboratory at MP. So now it's a company, but eventually all the people that are the people that made, that were working at MP. I think the reason why it is a company is just because it's probably more managing, from the managing point of view, it's more cost effective to run a thing like this as a company rather than as an institute, a research institute. But for instance, in Japan, the CCDs on Japanese mission, they are created by the Hamamatsu company, yeah. So it's they're private undertaking.
But there's something different that has to happen to promote the efficiency of detection of X-rays as opposed to optical photons.
You mean technological?
Yeah. Or it,
yes, yeah. Yes, but I don't know exactly which answer you want from me.
yeah. And just one follow-up is, what is the charge transfer efficiency of the X-ray CCDs? Because in the optical, we're used to what we call 4 nines, which is 99.9999% CTE.
Yeah.
Is it as high?
It's no, each step is very low. It's 10 to the minus 5, if I remember
So
correctly. Yeah, but we have large arrays of pixels.
Yeah.
So, and we have many photons. Sorry, we have many electrons. So eventually, the number of electrons that we lose when you integrate over the whole row of columns, it's not negligible. It's an effect. It's an effect that at the readout node is of a few percent in case of cement. So you need to calibrate it if you want to achieve. We want to achieve accuracy of the energy reconstruction, which is of the order of 10 eV in principle. So it's 10 eV are 3 electrons. So you can easily lose much more than 3 electrons. So yeah, it has to be calibrated as well. And it's energy dependent, all kind of things.
Does that change according to the source very much?
Yeah.
Reduce your, what is the typical transfer time for
yeah, it depends, of course, on which one. So for the, I think I have the numbers here. For instance, that's an example for, just as an illustrative example for the CCD on board XMM Newton. So I don't use shortenings. So in the largest frame, so the slowest mode is of the order of between 70 and 100 milliseconds. And in the timing mode, which is the fastest, is 7 microseconds. For the other CCD camera on board XMM Newton, it's sort of similar ballpark. Christine, new star timing resolution? It's not microseconds, and new star is seconds. Yeah. No. Sorry. This is just this is just the time between run with readout and the next. But then the observation can continue for hundreds of kilosecond hours, days. You just accumulate the. So essentially, as Aitor probably is going to show you later, basically all the missions, I think this is applied to all the missions we're dealing with in this workshop. We work with event lists. So for each event, we have one row in a large table, which contains all the properties, the location, the energy, the time, and so on. And once you have the list of events, then you can do whatever you want. So you're not limited by the fact that we accumulate just images and we forgot how the image was created. We can exactly reconstruct when each event happened and reanalyze, repost the process of events to create any type of scientific models on ground.
That image you see there on the left side, it's probably an image taken for 20 hours. You're accumulating 20 hours, and in many of these readouts, there is not a signal in your main, but when you put everything together, you stack everything together, you see.
The time resolution of about 200 minutes.
Yes.
And the
So,
resolution is 200 milliseconds for each photon.
Yeah. So essentially, you can distinguish two photons that hit the detector at the time separation of 70 milliseconds. And in fact, 70 milliseconds is very important in say astronomy. It's really much better than very regular.
Further questions during the coffee break? We are taking for 15 minutes. So be back.